So what do you do when the water is just entirely too deep for a traditional fixed structure to reach the seabed? Say you're operating in water depths of 500 meters to 1,500 meters, but the highly sensitive equipment you're using absolutely cannot handle the violent up and down bobbing motion of a regular boat. It's a massive challenge. I mean, how do you build what is essentially a skyscraper in 1,500 meters of water?
Welcome to The Explainer. Today, we're going to be looking at the brilliant engineering design that solves this exact deep-water dilemma: the tension leg platform, or TLP for short. It's a fascinating hybrid design that really defies the traditional rules of offshore engineering. Let's get right into it.
Here's our quick roadmap for today. We're going to start with the deepwater dilemma, actually meet the TLP, break down the physics of tension, check out the rigid riser advantage, look at some real-world giants in the Gulf, and then finally, we'll wrap up by discussing the absolute limits of this technology.
Okay, starting with Section 1, the deepwater dilemma, where we are really pushing the limits of fixed structures.
To really appreciate what the TLP does, we first kind of need to understand the limitations of traditional offshore engineering. You see, fixed platforms are great, right? They offer this perfectly static, stable environment where your equipment just doesn't move. But they have a really harsh physical limitation. The deeper the water gets, the heavier and vastly more expensive the steel jacket structure becomes. And it's not just a linear increase, it goes up exponentially. Since wave forces increase with depth, the structure has to resist these massive overturning moments from decades of storm waves. Honestly, once you hit about 400 meters of water, a fixed jacket is pushing the absolute limits of what's economically and physically possible.
So obviously, if you can't build a fixed tower from the seafloor up, you have to float. But floating introduces a completely new enemy, and that enemy is heave. Heave is that violent, vertical, wave-induced motion. You know, the literal bobbing up and down you feel when you're out on a boat. And let me tell you, heave is the absolute worst enemy of deep-water oil and gas production. When you've got these long, rigid pipes trying to connect a moving floating facility to a perfectly fixed wellhead down on the seabed, well, violent vertical motion is just going to completely destroy your equipment. We essentially needed a way to float, but completely without the heave.
Which brings us to Section 2. Let's officially meet the tension leg platform, the ultimate hybrid of floating and fixed.
Okay, let's dive into this anatomy. This is the engineering hybrid that perfectly bridges that gap between a free-floating vessel and a rigid, fixed installation. A TLP is a floating structure, typically a semi-submersible hull with pontoons and columns, but the magic is beneath the water. It's tethered directly to the seabed by these massive, vertical, tensioned legs. These tendons, or tethers, are usually huge steel tubes or incredibly heavy wire ropes. They run straight down from the platform's corner columns and lock into these massive foundation templates that are literally pinned deep into the seabed.
Moving on to Section 3, the physics of tension. This is what I like to call the reverse anchor paradox.
So, how does this setup actually stop the platform from bouncing around in the waves? Think about a normal boat. It sits on top of the water, and an anchor pulls it down to keep it from drifting away, right? Well, a TLP flips this entirely. The key insight here is that the TLP is deliberately designed to be overwhelmingly buoyant. Even when it's fully loaded with thousands of tons of equipment and crew, it desperately wants to float much higher than those tendons will actually allow it to. Because it wants to pop up to the surface like a giant cork, those tendons are kept under immense permanent tension. They are constantly pulling down on the hull, while the hull is constantly pulling up on the seabed templates. Hence the name, tension leg platform.
And the result of all that tension? Just like our sources point out, the platform doesn't bob up and down with waves the way a ship does. That constant extreme tension in the vertical direction virtually eliminates that vertical motion. It's totally locked out. Now, to be clear, the platform can still sway side to side or surge forward and back, and it can even tilt or pitch slightly with the wind and the ocean currents. But that destructive vertical heave, it's just gone.
All right, Section 4, the rigid riser advantage. Let's talk about why locking out that vertical motion is such a massive deal.
So why does controlling heave matter so much? It all comes down to the risers. Those are the pipes that actually bring the oil and gas from the seabed right up to the platform. On a standard floating production ship like an FPSO, the ship moves vertically with the waves. Because of that, you are forced to use these highly complex, flexible, steel-reinforced risers. They basically act like a massive slinky to absorb all that wave motion. And they are unbelievably expensive, they're prone to hydrostatic collapse in deep water, and they come with a really heavy maintenance penalty. But on a TLP, because the heave is strictly controlled, engineers can run simple, cheap, and highly reliable rigid steel risers directly from the subsea wellheads straight up to the platform. It is a massive operational and economic payoff. Now for Section 5, Giants of the Gulf. This is where we see this theory translated into massive, real-world scale.
Okay, so we know the physics work, and the economics definitely work. Let's look at the real-world evolution. The Conoco Oil Company actually devised the TLP concept, and they built the world's very first one for the Hutton Field in the North Sea back in 1984. It was in just 148 meters of water, so it acted as this perfect, harsh environment testbed. Then, a decade later in 1994, the Auger TLP was installed in the Gulf of Mexico in a massive 872 meters of water. Auger proved that TLPs were a highly viable solution for deepwater production. And from there, the Gulf of Mexico essentially became the primary testing ground for TLP technology. That led to absolute giants like the Shell-operated Mars and Ursa platforms, which are among the most productive deepwater platforms ever built. We even saw massive concrete variations hit the water, like the Hydron TLP in 1995.
Actually, to really grasp the sheer scale of these structures, let's look at that Hydron platform for a second. Because the platform is constantly pulling up with such incredible force, it needs to be anchored to the seabed with some serious weight. The Hydron TLP uses 4 concrete foundation units on the seafloor to secure its tethers. To put that into perspective, just one of those 4 foundation units weighs a staggering 21,000 tons. I mean, 21,000 tons. It's 48 meters across and 26 meters high. Just for one unit. That right there tells you the sheer amount of force required to hold these buoyant giants down.
Now, obviously, not every single oil field out there requires a 21,000-ton anchor, right? For smaller fields and moderate water depths, engineers came up with the mini TLP. These are much smaller, single-column structures, like the famous Sea Star design. They're brilliant because they offer those exact same stability advantages. Locking out the heaves, you can still use rigid risers, but they do it at a mere fraction of the cost of their massive multi-column big brothers.
Finally, Section 6, the limits of TLPs. Let's talk about the engineering trade-offs.
Because look, no engineering solution is absolutely perfect, right? Everything has a cost. With TLPs, the most pressing limitation comes down to safety and fatigue. These tendons are highly critical components, and they are under constant extreme fatigue loading. Think about it. They're essentially massive steel rubber bands, constantly fighting the extreme buoyancy of a hull while also taking the lateral crashing of ocean waves day in and day out for 25 years or more. A tendon failure could have catastrophic consequences. Because of this, they have to be designed, manufactured, and inspected with an extreme level of care. There is just zero margin for error here.
The second major limitation is flexibility. As our sources point out, unlike an FPSO, a TLP is largely committed to one site. When you install a floating ship, you can eventually just unmoor it and sail it over to a newly discovered field. But once you have driven tens of thousands of tons of concrete and steel into the seabed to lock down your TLP, yeah, your multi-billion-dollar platform ain't going anywhere. It is thoroughly committed to that specific location. They are just not easily relocatable.
Which leaves us with a pretty fascinating final question for today's explainer. What if you actually do need to move your rig to a new field? What if you need that extreme deep water capability of a floater, but you want the mobility of a ship, entirely without the permanence of a TLP? Well, to do that, you're going to have to rely on the versatile giant of the offshore world, the semi-submersible. And we're going to dive into exactly how that structure works in our next explainer. Thank you so much for joining me today, and keep learning.